Hello Philo Math, I am Dr. Vilva and meet my friend Vrinda.
Hi, you just found me in UK, that is unknown to known channel. Here, numbers stop being scary and start to say story. Let us involve, learn and win.
The very first chapter is on real numbers. In this video, we are going to discuss Euclid's division algorithm and its applications, the fundamental theorem of arithmetic and its applications, and a few related problems. Euclid's division algorithm states that any positive integer a can be divided by another positive integer b. This process leaves a remainder r which is always strictly smaller than b. We can write it as a equal to b times q plus r. Here q is quotient when a is divided by b and r is a remainder. Also, the value of r can be 0 to any integer that is less than b.
Vilma, can you pass now? I couldn't follow what you just said. All of a sudden, I feel like you started talking in Greek.
Let me fix that with an example, Vrinda. For example, 14 is divided by 4. Here, a is 14 and b is 4. You can write 14 as 4 times 3 plus 2. Where did the 3 come from? When 14 is divided by 4, the quotient is 3 and the remainder is 2. Therefore, 14 is equal to 4 times 3 plus 2. Also, the remainder r is 2 which is exactly less than b, that is 4. 2 is less than 4. Let us look at another example. Divide 219 by 11. A is 219 and b is 11. The quotient is 19 and the remainder is 10. Again, 10 is less than 11. I hope that makes sense now.
Is it necessary to know this theorem?
Of course, my dear. This theorem has many applications. One of them is computing the HCF, highest common factor of any two positive integers. I will show you how to find the HCF of 219 and 11. First, we will write 219 in the form of bq plus r using Euclid's division algorithm. 219 is 11 times 19 plus 10. Here, 219 is a dividend, 11 is a divisor, 19 is a quotient and 10 is a remainder. The old divisor becomes the new dividend and the old remainder becomes the new divisor b. Old divisor is 11 and the remainder is 10. Now 11 can be written as 10 times 1 plus 1. Remainder is 1. Therefore, we will repeat the procedure. We repeat the procedure until the remainder is 0. We take 10 and the new remainder 1. 10 can be written as 1 times 10 plus 0. Now the remainder is 0. Therefore, we will stop the process. The divisor at the final stage is the HCF. Therefore, HCF of 219 and 11 is 1. Another important theorem is Fundamental Theorem of Arithmetic. It states that every composite number, that is a number which is not a prime, can be written as a product of prime numbers. The product of prime numbers, we call it as prime factorization, and it's unique apart from the order in which the prime factors occur. To make this clearer, let us look at an example. We can factorize 42 as 2 times 3 times 7. This is equivalent to 2 times 7 times 3, apart from the order of writing those prime factors. If you notice, the prime factors in both the cases are 2, 3 and 7, but the order is different. To standardize the factorization and make it look truly unique, we write the primes in ascending order. I have included a few more examples for your reference. Also, using this theorem, we can prove that many numbers are irrational, like root 2, root 3, etc. Additionally, we can use it to determine whether the decimal expansion of a rational number is terminating or non-terminating and repeating. Vrinda, I hope everything makes sense to you now.
Of course, ma'am. Now, numbers aren't so scary. They tell me an interesting story. Let us have some fun and work on some applications problem, ma'am.
Here we go to have a real fun. Let us check whether there exists a value for n such that 4 raised to n ends with the digit 0. For a number to end in 0, its prime factorization must include both 2 and 5. However, if we look at 4 raised to n, we can write it as 2 times 2 to the power n, which equals 2 to the power of 2n. The only prime factor here is 2. Since 5 is not a prime factor of 4 power n, the number can never end in 0. We can see this in action. 4 raised to 1 is 4, 4 raised to 2 is 16, 4 raised to 3 is 64, and so on. None of these end in 0. Therefore, we can conclude that no natural number n exists such that 4 power n ends with the digit 0. We are almost at the end of chapter 1.2. We will quickly look at how to use the prime factorization method to find the LCM and HCF of any two integers. Let us find the LCM of 12 and 126. 12 is an even number. Therefore, it is divisible by a prime number 2. 12, when it is divided by 2, it leaves a quotient 6. 6 is an even number again. We can divide it with 2 with a quotient 3. 3 is a prime number. We will stop the process. Therefore, 12 can be written as 2 times 2 times 3, which is the prime factorization for 12. In the similar manner, 126 can be written as 2 times 3 times 3 times 7. When comparing the prime factors of these two sets, 2 and 3 appear in both the sets. Since these prime factors are common to both numbers, we only write them once when calculating the LCM. We then include the remaining factors 2 from 12 and the 3 and 7 from 126. Therefore, the LCM is 2 times 3 times 2 times 3 times 7, which is 252.
What is LCM, Villu? For God's sake, don't just say it stands for least common multiple. You know I'm not asking for the abbreviation.
Let me put it this way. We just found the LCM for 12 and 126, which is 252. If you look at the multipliers of 12, 12 times 1 is 12, 12 times 2 is 24, goes on, we will get 120, which is 12 times 10, 132, which is 12 times 11, etc. And eventually 252 appears when 12 is multiplied with 21. On the other hand, if we look at the multipliers of 126, we have 126, which is 126 times 1, and 252, which is 126 times 2. When you compare these two lists, 252 is the smallest or least number that appears in both. That is what least common multiple truly means. When you multiply 12 and 126 by various integers, 252 is the first time the result match. I hope that makes more sense now.
Oh, it's clear now. Will you teach me to find HCF using same technique?
For the same integers, let us find the HCF. 12 is 2 times 2 times 3 and 126 is 2 times 3 times 3 times 7. Looking at these two factorization, the common factors are 2 and 3. To find the highest common factor, we only consider these common prime factors. Therefore, the HCF of 12 and 126 is 2 times 3, which is 6. To put it simply, the highest common factor is the largest number that divides into both. If you divide 12, the possible divisors are 1, 2, 3, 4, 6 and 12. Similarly, for 126, the divisors are 1, 2, 3, 6, 7, 9, 14, 18, 21, 42, 63 and 126. If you check these two lists, 1 is common between these two, 2 is also common, 3 is also common, 6 is also common. But 6 is the winner. That is the highest number that appears in both lists. So, the highest common factor is the largest integer that divides both numbers exactly.
Everything is fine, but why should we learn all these things?
We need to learn LCM because it is essential for adding or subtracting rational numbers, that is, fractions. You cannot add rational numbers the same way you add integers. You need a common denominator, that is, LCM. On the other hand, HCF is also necessary to simplify rational numbers to the lowest term. For example, 2 by 4 is a rational number, but it is not the simplified one, but 1 by 2 is. How do we get 1 by 2? For 2 and 4, common factor is 2. We have divided 2 by 2, 4 by 2. So we will get 1 by 2. But the real fun begins now. Let us look at some properties of LCM and HCF. The first major property is the product of the HCF and LCM of two numbers is equal to the product of the two numbers themselves, that is A and B. To cross-verify the property, we will go back to the previous example. Here, A is 12 and B is 126. A times B is 1512. Also, product of LCM and HCF of these two numbers gives 1512. We will see some problems based on this property. In this problem, we are asked to find the HCF of 106 and 358 using the prime factorization method and then find the LCM using that result. We'll see the solution. The prime factorization of 106 is 2 times 53. 53 is a prime number. Also, the prime factorization of 358 is 2 into 179. Again, 179 is a prime number. The only common prime factor between these two integers is 2. Therefore, the HCF is 2. Now, instead of using prime factorization to find the LCM, we can use this property. HCF times LCM equal to A times B. Plugging in our number, HCF is 2, that is 2 times LCM equal to 106 times 358. If we simplify this, we will get the LCM, which is 18,974. The beauty of the technique just we learnt is it also gives HCF and LCM of any number of integers. Let us find HCF and LCM for any 3 integers. For example, we are considering 48, 120 and 204. By writing the prime factorization for each integers, the product of the common factors gives us the HCF, which is 12. The LCM can also be found using prime factorization by multiplying the common factors with the remaining unique factors. An important point to be noted: the product of HCF and LCM of A, B, C is not equal to product of A times B times C. This property is applicable for 2 integers but not for 3 integers. Here are a few tips to help you factorize any integers. If an integer ends in 0, 2, 4, 6 or 8, it is divisible by 2. For the number 3, you can add the each digits of the number together. For example, in the number 18, the digits are 1 and 8. 1 plus 8 is 9. Since 9 is divisible by 3, 18 is also divisible by 3. As we have discussed before, if an integer ends in 0 or 5, it is divisible by 5. Additionally, if an integer ends in 0, it is also divisible by 10. We are at the end of the session. I have included a few practical questions for practice. First problem: imagine 2 colored lights. A red light flashes every 8 seconds and a blue light flashes every 12 seconds. If they flash together right now, how many seconds will pass before they flash at the same time again? To solve this, simply find the LCM of 8 and 12. Second problem is a rectangular floor that is 60 inches long and 42 inches wide. If we have to cover it with the largest possible square tiles without having to cut any of them, we need to find GCD, which gives you maximum size of the square tile. Give these simple questions a try. If you have trouble solving any of them, just leave a message in the comment section. We will go over the solutions and discuss your answers in the next video. Thank you all. Let us involve, learn and win.